Now, students, Bismillahirrahmanirrahim. We are now solving unbalanced networks. Unbalanced networks. What are unbalanced networks? Where basically the impedance of on any phase is different from other impedance, right? That is unbalanced. So remember, in unbalanced, the relationship that is line current is not equals to phase current, whether it is star connected, and line voltage is not equals to phase voltage in delta connection. This statement is true for unbalanced networks. The currents are not equal because the load is unbalanced, because every load draw different current. So line current not being to phase current in a star connection, and line voltage not being same to the phase voltage in delta connection. Remember this. Now start. So our in this case, each phase has different current, that is respective phase voltage divided by respective impedance. Similarly, because it is unbalanced, the second phase current is respective phase voltage divided by respective impedance, and similarly for the third current, respective phase voltage divided by respective impedance. Remember, in unbalanced networks, neutral current is not being zero. In balanced, neutral current being zero, and we can remove neutral in balanced system. We can remove, yes, but unbalanced system, no, we cannot remove the neutral, because neutral has some current, and that is nothing but the sum of all three currents with negative sign. Sum of all three currents with negative sign. So this one is unbalanced Y load. See, this one is Y connection. This one is line A current. This one is neutral current. This one line B current. This one is line C current. This one is impedance of line A, impedance of line B, impedance of line C. The common point is neutral. And if you see, all the currents are flowing towards their respective phases, IB, IC, IA, right? So the has the balance voltage. The condition is given. The balance voltage of this network is 100 volts, and the sequence is ACB. Remember this. In this, the sequence is changed. That is ACB. Before we are doing the phase sequence, we have practice of ABC. Now the phase sequence is changes to from ABC to ACB. In this question, particular question, the phase sequence is ACB. Calculate the line currents and the neutral current. So in this case, you have to calculate the line currents. Line currents, that is IA1, IA, IB, and IC, the line currents, and the neutral current. That is, in this case, neutral current not being uh, zero because unbalanced. And we have given the values of impedance, that is ZA is given to us, that is 15 ohms. ZB is given to us, that is 10 plus J 5 ohms, and ZC equals 6 minus J8 ohms. So let's start the solution. So what is line current? What is line current? So line current is nothing, it's the ratio of voltage over impedance. So voltage is 100, 0 degree, and the impedance of ZA, that is phase A, was 15 ohms. So it is a ratio of voltage over impedance. So when you take the ratio, you will get 6.670 degree. Why 0 degree? Because it is reference. The first phase is termed as reference, right? So what is the second current? That is IB. This one was IA, right? The second current is again the ratio of voltage over impedance, but 120 degree apart. 120 degree, that is IB, over impedance of the phase B, 10 plus J5, right? So when you solve this phasor, you will get 8.94 angle 93.44 degrees. The unit is amperes. The unit is amperes, right? And what is the third current? That is IC. The third current, IC. Again, the voltage being same. The third phasor is either you take 240 or minus 120, because if you take third phase representation of second, it is my 120 apart, if it take with the first, then it is 240 apart. So minus 120, the angle is minus 120, right? And the impedance was 6 minus j8, so it becomes 10 angle minus 66.87 amperes, right? So we have all the, see the line currents are different. The line current of line A is 6.67. The line current of phase B is different. Why? Because impedance of each line is different. That's why this is unbalanced. Impedance of each line is different. So if you apply Kirchhoff current law, see, this one is a node neutral. This one is a node. So the current flowing towards the node, right? What is Kirchhoff current law? Current entering is equals to current leaving, right? Or entering current and leaving current. The algebraic sum of all that is equals to 0. So the neutral current beings minus of AA, IB plus of IC, right? So we just calculate all these currents. Just put the values. You will get the current, that is 10.06 angle 178.4. See, the neutral current being not zero because unbalanced. Because unbalanced, neutral current is not zero. So in this problem, for the unbalanced circuit as shown in this figure, find the line currents. You have to find the line currents IA, IB, IC, right? Find the line currents, the total complex power absorbed by the load, the total complex power absorbed by the load, and the total complex power supplied by the source. Total complex from the source. This one is load. In this circuit, in this diagram, you can easily visualize that the load impedance. See, this one is inductive reactance, this one is resistive, this one is capacitance. So each phase, each load have different amperes, right? Not same, means IA different, IB. So this is unbalanced, right? The nature of load is unbalanced. So this is unbalanced network. So we use mesh analysis to find the required currents, right? We use mesh analysis. See, in this one is complete mesh. Mesh means closed path. This one is mesh 1, this one is mesh 2. So use mesh analysis to find the current. For mesh current I, if you write, if you start 120 minus 120, right? Starting the current enters into the positive terminal, then minus 120, the current enters into the negative terminal, 0 degree, right? Then plus 10 plus J5, because the impedance is J5 ohms, right? And the resistance is 10, right? The sum of these two. 10 plus J5 minus 10 I2, right? Because difference of current, see, I1 and I2. Here the I1 current, here I2 current flow. So according to mesh, the difference of current flow, so minus 10 I2 is equals to 0. Is equals to 0. So when you arrange this, you will get 10 plus J5 I1 minus 10 I2 equals 120 under root 3 30 degree. Recall the phasors. In delta connected, the respective line voltage is ahead of phase voltage by 30 degree. So 120 under root 3 times 30 degree, right? The voltage can be written like this. Similarly, for mesh 2, you may write for mesh 2, that is this one, mesh 2. What is the equation being? It is 120 degree, right? Current enters into the positive terminal, so 120 degree, right? Then this current enters into the negative terminal, then minus 120, and the angle being minus 120. See, this mesh covers this source, right? Plus 10 minus j 10 I2 and minus 10 I1. Again, because we are writing mesh 2 equation, so mesh 2 current supposed to be greater than mesh 1 current. So difference of current, that is minus 10 I1. So this one is a mesh equation. Rearrange it. Again, same thing. The second one is the voltage, the RMS voltage is 120 root 3 times angle of minus 90 degree. So just make the determinants of these two. Means you have to solve. This one is equation 2, right? Before it was mesh 1, so it was that was equation 1. So just solve these two equations. So you need to solve mesh 1 and mesh 1 and mesh 2 equation. You need to make the determinants, that is 10 plus j 5, that is coefficient of I1 minus 10, right? Then coefficients of I2, that is minus 10 j minus 10, right? See, I1 I2. So on the right hand side you need to write the constant. The first constant was 120 under root 3 times 30 degree, and the second constant is 120 under root 3 minus 90 degree. Okay, so these are constant and these are current I1 and I2. So you may know this rule that what is I1? I1 is del 1 over del, and what is I2 is del 2 over del. So del 1 matrix, you just need to remove the first column with the constant. You will find the del 1 matrix. What is del matrix? Del matrix. This one is del matrix actually. This one is del matrix. This whole one is del matrix, right? So it is your job to calculate del 1 and del. So I'm writing the values, that is del 1 comes out to be 207.85, 13.66 minus j 13.66, and the del matrix comes out to be 50 minus j 50, and its phasor form is 70.71 angle minus 45 degree, right? And del 2 comes out to be 207.85, 13.66 minus j5, so del 2 comes out to be 30 3023 angle minus 20.1 degree. So what was the formula? I1 was the ratio of del 1 over del. We already calculated the values of del 1 and del. Just put the values, that is 4015.23 angle minus 45 over del, that was 70.71 angle minus 45. So it comes out to be 56.78 amperes, because it is mesh 1 current, right? Amperes. Similarly, I2, that is mesh 2 current, it was the ratio of del 2 over del, and it was 23023.4 angle minus 20.1 over 70.71, because del being same in both the cases, the del being same, right? So it comes out to be 42.75 angle 24.9 degree ampere. The unit of current is ampere, right? So the line currents are the line currents, that is IA equals to I1. The magnitude of that current is 56.78 ampere, right? And IC equals minus I2. If you see the figure, I rub that figure when I consider that figure, the direction of the current of IC and I2 are opposite. So that's why IC is designated as minus I2 by considering figure, right? So it becomes 42.75. The magnitude being same, the direction are opposite. The angle minus 155.1 degree amperes. And IB is the difference of two currents, that is I2 minus I1. If you consider the figure again, the direction of I2 and I1 was opposite, right? I2 and I1, the direction of both the currents are opposite. So the difference of these two currents from this line, that is line B, the difference of these two currents, right? So in this we calculate all line currents, that is line A, line B, and line C. All line currents are calculated. As we calculated all the line currents, now we can calculate the complex power absorbed by the load. So what is the complex power absorbed by the load? SA. Remember, the uppercase used for load and lowercase is used for the source. So complex power absorbed by load, SA, equals line current magnitude square times line impedance, right? What is power? Remember, I square times Z. So in this way, we already calculated our line current, that is 56.78 square, and the impedance of phase A was J5. So the power absorbed by load A equals J 16.120 volt ampere. The units being volt ampere because apparent power, right? For phase B, for phase B, similarly, phase B current square times phase B impedance. Here I am writing the answer, not because you know the values. So this comes out to be 6480, 6480 volts ampere. Similarly, complex power absorbed by load C is the current square times the respective impedance. So it becomes minus J 18.276 volt ampere. If you noticed, your phase B was resistive, so the volt ampere, right? It was inductive, so plus J. It was capacitive, so minus J, right? Phase A was inductive, phase B was resistive, and phase C was capacitive. So minus J shows to you capacitive, right? The total complex power absorbed by the load is what? The total complex power absorbed by the load is nothing but sum of all. Sum of all. So when you sum up all the power, you will get 6480 minus J 21.56 volt ampere. Remember, apparent power is measured in volts amperes. Now it's last part. We have to calculate the power supplied by the source. So power supplied by the source, power supplied, that is apparent power supplied by the source, that is SA. It is also different because every current is different. So it is nothing but, because it is supplied power, so negative sign, right? Previously we do this problem also, some other problem we discussed this. So this is minus V, because it is supplied power, so it is negative, minus Vn times the current conjugate. And Van, it was given to us in the problem 120, 0 degree, right? And the current conjugate, because it was only the current have the real part, so only magnitude of current is taken. So it comes out to be minus 6813.6 volt ampere, right? Similarly for source B minus VBN, minus VBN IB conjugate, so it becomes minus 120, minus 120 degree angle. And when you take the conjugate of current B 25.46, before it was plus 135 because conjugate, so minus 135. So SB becomes 790 minus J 2951.1 volt ampere. And similarly SC again minus VCN and IC conjugate, right? So put the values, minus 120, uh, plus J 5109.7 volts ampere. So the total complex power supplied by three-phase source is nothing but the sum of complex power supplied by C, B, and A. That is sum of SA, SB, and SC, you will get the total power supplied by the source. So the total power supplied by the source is equals to SA plus SB plus SC. So when you sum up all, you will get minus 6480 plus J 21 point, sorry, 2156 volt ampere. Or if you sum up this power, that is source plus load, it becomes zero, right? Because whatever source generated is equals to load if we neglect transmission lines. So if we sum up these two, we'll get zero. You can verify this. Thank you. So this chapter becomes end. Polyphase becomes end. I will give you the numericals, then the practice problems to you as an assignment, and you will do practice from that assignment. Also, you can do drill problems of William Hyde. Chapter 12 is polyphase circuits. So in the next class, we start magnetically coupled circuits. Our polyphase circuits becomes ends. Good luck.